So just noise are also referred to as thermal noise, resistance noise, or white noise. Okay. So just summarize. It is independent of the composition of resistors, and the frequency distribution of thermal noise power is uniform. That's why I mentioned from low frequency to high frequency, the noise power is the same. Okay. Okay. The instantaneous amplitude for thermal noise has a Gaussian or normal distribution. So average is 0, and the RMS value is given above. So so the noise is looks like you have a for example, you have a noise power some above 0, some below 0, because they happen randomly. Okay. So if one to add them together, they become 0. I mean, if you consider it as like a voltage, it go up and down, and some beyond 0, some below 0. Add them up together, the final amplitude is 0. But that means so maybe you think the add up is 0. Maybe there's no effect, but that's not true, because when they come into your circuit, you consider the noise power is not only the noise level itself. So when you consider noise power, you square up. You took the root mean square of the whole, signal. So for those signal under 0, they become positive. So it becomes part of noise power. So you have a lot of noise. So that's a reason for this kind of noise. You cannot cancel them out by just design 4 different resistors inside the crystal bridge. It's not going to be cancelled out. So the noise, when you have a 4 resistor coming together, no matter what kind of your arrangement of the resistor, you can arrange them in parallel, you can arrange them in serial, but the junction noise, you need to add them, the noise power, you need to add them together. Okay? They cannot be cancelled out. Okay, because they are happen randomly in individual resistors. Okay, understand? So maybe you think that you have a symmetry design of your resistor. So what happened on the left hand side, maybe you have similar noise on the other side. So maybe you think that you put them together, you can cancel out the noise, but it's not true. There's no way, because what happened in the left hand side is independent to what happened on the right hand side. So the noise happens independently on individual resistors. Okay? They are independent in time. Okay? So you cannot anticipate what kind of noise you can have for each of the individual resistor. So that's why every time when we calculate the total noise, we need to add all the resistors noise together, become the final noise. Okay? They cannot be cancelled out. Okay? So we will see that in more detail later when we put into the real numbers, okay, into the design. So you will get a better idea. So, yeah. Okay, so this is the first noise I would like to talk about. So the noise has been changed into the voltage form, okay? Then we will consider another noise we call the mechanical noise, our thermal noise equivalent acceleration. It is a kind of mechanical noise. The TNEA noise, the thermal noise equivalent acceleration coming from actually also the environment. You put the accelerometer inside the environment with a lot of gas molecules bumping onto the structure. So because the system is like a second order system, the system considers spring, a mass system, and using a cantilever to hang on the side. So so when the molecule hit onto the the plate of the proof mass of the thermometer, they also contribute noises. So the noise power similar to the Johnson noise is a kT over 2 because it has 3 different direction vibration. So finally, these are the effective RMS diffraction. Okay, because it's a cantilever system, so we're using the diffraction, the spring, the potential energy to represent this kind of noise power. So noise power is kT over 2, and equivalent to, if you consider a spring, if you store this noise inside a spring, the spring will deform, right? The spring, the 弹簧会变形. Okay, so when the spring deforms, that means the kinetic energy has been stored inside the spring, become the potential energy. Okay, so the kT over 2, this is the kinetic energy from your noise, and now transfer into the spring. Okay, stored inside the spring. So the spring will be x means the vibration distance. Okay, that's the change of the elongation of the spring, for example, times the spring constant over 2. That's RMS diffraction. And also this noise power, you can do some calculation very similar to Johnson noise. You can end up find out the equivalent acceleration will be 4 kT omega n over the mass times the quality factor of the system. Okay, so we have talked about a little bit about friction response. That means how fast the spring can go, how fast the accelerometer, the sensor, can go with your signal, and the omega n equal to your spring constant over the mass and the square type. Okay, the 4 kT are also similar to the Johnson noise. So this noise also depends on the temperature. You have a higher temperature, you also have a higher acceleration equivalent noise. And it's inversely proportional to the square of your mass. So you have a large mass, you can reduce the noise as well. Okay, so you have very heavy proof mass over there. The hitting of the molecule onto the mass will not give you a strong effect because you are very big. So the interference is not that high from molecule. So if you increase the mass, you can reduce the noise power as well. And also the quality factor. So you have a high quality factor, you also will reduce noise power. But also you have a large omega n, omega 0, that means you have a large window. This idea is similar to Johnson noise. Omega n means that your frequency response also means your window open up for the noise. Okay, so the window means you have a high frequency response system. So the signal, no matter coming from the low frequency or high frequency, will be accepted by the system to become a noise. So omega n also means the window you open up for the system. Okay, so this is equivalent RMS acceleration. So when we look into this RMS acceleration and compare to the previous Johnson noise, the Johnson noise is represented readily in the voltage form. The voltage is the final result. We want to do the measurement, right? However, the mechanical noise is represented in the acceleration form. Acceleration means the input signal we want to do the measurement. Okay, so you want to put these two together to do the comparison. They are not comparable now because one is acceleration, the unit acceleration. The other one is the unit of voltage. So they cannot be compared. So if you want to do the comparison, you need to transform this acceleration into the voltage. How do you do? How would you like to do? The easiest way is by timing the acceleration equivalent noise with the responsivity, right? This noise equivalent acceleration times the responsivity, you got the final units become voltage. Remember, the definition of responsivity is the output voltage over your input acceleration, right? So now we have the acceleration here. So we want to transfer this acceleration into the final output voltage. So we use this acceleration equivalent noise times with the responsivity. Then we got the final voltage, okay, coming from this noise. Do you understand? OK， 因为 responsivity 它基本上是那个我的 output voltage 除以我 input 的加速度，对不对？你这边的单位是加速度，所以乘以 responsivity 以后，你就得到 voltage。OK， 就这个加速度最后看到的 voltage 是多少？好，这是最简单的做法。这样弄完以后呢，它得到的是 voltage， 就可以跟前面的 Johnson noise 做 comparison。所以你要做比较的话，either就是把前面那个除以 responsivity， 要不然就是把后面这个乘以 responsivity， 他们就可以做比较了，换成同个单位就可以做比较。Okay, so we transfer them into the same units, then we can do the comparison. So we will see in more detail later on. Okay. Okay, so after consider these two parts, now we go to the sensitivity. So the sensitivity is different from your thinking. Okay, actually the sensitivity means the lowest signal you can detect in a system. The lowest signal you can detect in a system. When we define the sensitivity of a sensor, so in this case, the sensitivity will be the total sum. We add all the noise together. What is the final noise level of your system? There will be your sensitivity, because your signal cannot be lower than your noise level, the noise floor. Okay, the sensitivity. So sensitivity, that means after you add all the noise together, will become there will be a value of the voltage, the noise equivalent voltage. So your signal need to be larger than the noise equivalent voltage. Then you can do the detection. Otherwise, you cannot do the detection. The sensitivity, that means that the low, signal, the lowest signal you can detect. That means the noise floor. Okay. 这边的敏感度代表是最低你能够量到的讯号，最低能够量到的讯号就是所有那个noise， 就是你的这个杂讯加起来的结果。OK， 你的讯号不能低于杂讯，低于杂讯就看不到。好，所以所有的杂讯我们后面会加起来，前面至少讲了2个杂讯，事实上有3个杂讯哈，全部加起来的结果，我们的讯号这是最低能够量到的，就那样。OK。Okay, so this is sensitivity. Now we consider dynamic range. So dynamic range, that means the lowest signal and the highest signal, there is a range between them. So between the lowest signal and the highest signal, this is the range you can do detection. The sensor is working, okay, in this range. Okay. Beyond these two range, you cannot do detection. That means if a signal below this is lowest signal, because the noise over there, so you cannot do detection. And if a signal above this signal, the system may be damaged. It also cannot do detection as well. So there's a range between them you can do measurement. So this range we'll call the dynamic range. Okay. So for dynamic range, the upper limit will be the strain limit. That means what's the when will the sensor become failure? Okay, so if you have a very large acceleration, you break the sensor, then the sensor cannot work anymore. So the upper limit means the condition when you input a signal too large, so the sensor break itself. So then now we will consider what kind of mode will make the sensor break. That means can never encounter some kind of the strain over its strain limit. It cannot deform too much. If it deforms too much over some kind of range, the sensor break. It can never break. Okay. So usually we'll consider fracture strength for silicon or semiconductor or ceramic-based material is roughly around 1%, very small. Yeah, so very different from like metal or even plastics. For metal, the strength limitation usually is around like 0%, and for polymer, it may be much more than 5%, even 10%. But for ceramic material or for like a silicon or silicon dioxide, silicon nitride, is roughly 1%. It's not pretty high. So if we put it into the strength limitation of 1% into equation 7-1-20, the fracture strength can be estimated, okay, as like this equation. And from this equation, the Zn over Ei, we also understand the moment, the bending moment will be your acceleration times the arm of the moment. Okay, so you can see the acceleration is embedded inside this equation. So you put all these parameters to the left-hand side. You can set up the fracture strength equal to 1%. So this one equal to 1%. Then you can calculate that your acceleration upper limit will be the fracture strength, the 1%, times the rest of the parameters. Okay, rearrange the parameter into left-hand side. So leave only A upper at the right-hand side. So the A upper will be the strength limit, that's 1%, times the rest of the parameter, the geometry parameters over here. So the A upper can be calculated. You can find out the upper limit in this kind of case is around like a 4 orders of magnitudes higher than your lowest signal you can detect. Usually, it's 3 order magnitudes or 4 order magnitudes. For typical mechanical sensor, the diameter range is usually in this range, 3 order to 4 orders of magnitudes of the sensing range. Okay, so we do the calculation later on, so don't worry. So you will find out the real value and you get some real physical meaning. So our upper limit will be the friction. Okay, so the lower limit will be the sensitivity, the higher limit will be the fracture.